In this last video on alcohols, I'm going to discuss how to convert alcohols to better leaving groups. So hydroxyl groups on their own, meaning just as an OH, are not good leaving groups. Right? You need to do something to them to make them a better leaving group. Now, first thing you could do is protonation with strong acid. This is something that works really well for HBr, not as much for HCl. So the next thing I'll show will be what can you do with HCl. So if I have my primary alcohol, and this would work for primary or secondary because it's going to be an SN2 mechanism. Got my HBr. Protonate the alcohol. So now it's water, right? And water is great on its own. So it's a very good leaving group. Bromide comes in and attacks via an SN2 mechanism. And you get your product. Now you can do something similar with chloride, but you need a catalyst. So you're going to have HCl and zinc chloride, and this is your catalyst. I'm going to use the same substrate. This reacts with the catalyst, zinc chloride. And now Cl- will come in from the HCl, right? That's why we have the HCl there. This will be the nucleophile, kick off the oxygen zinc chloride bond, to give the chloride. Right, it's very comparable to up here, just rather than a hydrogen, you just have a metal complex instead. But that's why both of those are excellent leaving groups. You have a positively charged oxygen in terms of formal charge, and when it leaves, it doesn't have a positive formal charge anymore. And as a very electronegative atom, oxygen doesn't want a formal positive charge. All right, third reaction that you could do is going to be with tosylate and pyridine. So for this reaction, you start with your substrate. This one again is going to be either primary or secondary because it's going to be an SN2 mechanism. You react with tosyl chloride and pyridine. And this transforms the hydroxyl to a better leaving group, OTS. Now notice here, there's no conversion of stereochemistry here. The real SN2 process comes in now when I add in the nucleophile. In this case, I'm going to do sodium iodide. Now I'll get the backside attack and the conversion of stereochemistry. So this will act like an SN2 mechanism does and invert your stereochemistry, even though in the first step there is no inversion. Because if there was inversion in the first step, the second step would invert again and you wouldn't end up with the inversion of configuration. So that's something to make sure to keep in mind. Number 4 is going to be reacting with SOCl2. This is going to be a way to basically transform a hydroxyl group into a chloride, which we know is a good leaving group. So simple substrate here, just ethanol. So this is the structure of SOCl2. The hydroxyl group, the oxygen comes in and attacks, electrons move up to the oxygen. Oops. It's a single bond now. Then I've got my two chlorides. Positive formal charge on the oxygen. The electrons in the oxygen move down and kick off one of the chlorides. So now I end up with that. Positive formal charge in the oxygen. Next, pyridine. We'll deprotonate the oxygen. And this all here is an excellent leaving group. So now I react with the Cl- that came off earlier. Right, we had one come off right there. That Cl now comes in with an undergoing an SN2 process to give the product. Now, if you wanted to convert to a bromine instead of a chlorine, you can use a different reagent, PBr3. So phosphorus tribromide. I'll use the same ethanol as my reactant. So I got PBr3. Comes in, kicks off one of the bromides. Notice again, positive formal charge in the oxygen. That bromide that got kicked off will now come in and react, and I end up with my product. So those are simple reagents that you can use if you're doing a synthesis problem and you want to ultimately remove a hydroxyl group. Use one of these reagents, switch it over to a halogen, and then it's much easier to remove as the halogen is a better leaving group.